So yes, indeed, welcome to my talk on testing Qt desktop applications. I'm Clare Macrae. I'm speaking to you from Cambridge in England, and it's an honour to have been invited to speak. Thank you very much. Just a quick high-level overview of the talk. It's predominantly about testing of Qt, but a significant part of what I talk about in the setting up testing, which is the bulk of the talk, is actually more generally useful, not just to GUI testing, but to testing large and complicated applications in general. So if you're unsure whether to watch this and not a Qt person, do stick around at least until the end of that section. I'll talk also about error-prone aspects of Qt code, because they're particular areas that you'll probably want to focus on testing. And I'll mention at the end briefly about using the approval tests approach and library with Qt code, and I'll explain more about that when I get there. Briefly about me, I started programming in C++ about the same time as I started programming with Qt, more than 20 years ago now. I've always been interested in testing, but in recent years, helping to share what I've been learning about sustainable and efficient testing has really become my main focus in working life, both when dealing with legacy code and when dealing with hard-to-test code. I'm the co-author with Llewellyn Falco of the approval test library for testing C++. I'm happy to answer questions via Twitter and email at any time, but for larger bodies of work, I'm also available for consulting and for training. There are a lot of links in this talk. You can get them from bit.ly/testingqt, from that QR code, or from that GitHub link, and those appear at the end of the talk as well, so don't worry if you don't catch them at this point. The nature of an online event is that I can't really feasibly answer questions during the talk, so there'll be a slot at the end to answer questions. If you've got any questions, pop them in the Q&A tab in Remo. If they relate to a particular slide, I'd really appreciate it if you could make a note of the slide number so we can get back to the right point. So here's a scenario that I've talked about before, but it's really important to understand the context. So the context here is you've inherited some Qt GUI code, and it's valuable. So you've been asked to make an improvement to it, perhaps add a feature or fix a bug. And you check whether it's got tests, and it doesn't. So therefore it wasn't designed for testing, and it's hard to add tests. So you would want to refactor it to make it testable, but you can't do that safely without tests. And that's the famous vicious circle when dealing with legacy code. And in this talk, my focus is on the right-hand side. So talking about when you have no tests and the code wasn't designed for testing, what can you do then? I'm going to help you break out of the circle at that point. Talking about strategies and patterns for refactoring, that's a whole other talk. There's not time for that today. So moving on to Qt. For anyone who isn't familiar with it, Qt is a at least 20-year-old framework, cross-platform graphical user interface application framework, a library. So many of the desktop and mobile applications that you're probably familiar with using will have been developed using Qt, and you can write your user interface on one desktop platform, and run it on all desktop platforms. It's really, really powerful library. But I firmly believe that Qt's graphical user interface powers do make automated testing harder. There's so much more to deal with than with testing console applications. And my goal for today is to give you the confidence to start testing your Qt application effectively and quickly as well. So let's talk about setting up testing. But before I do, I just want to mention a tool called Squish, which is produced by the FrogLogic company. It's an automated GUI testing framework for Qt applications. And typically, almost always, you would use it by running your entire application, and Squish tests the behavior of your whole application. It's a commercial tool, so not available for open source. Basically, the way it works is you sort of sketch out a scenario, a series of steps that you want to test. And then with the Squish tool running, you go through those actions in your Qt application, and Squish records your actions, the events that you've triggered, and saves them in the programming language of your choice. I'm familiar with Python, using it with Python. And then you refactor. The recorded events are no use for testing. They're dependent on screen resolution and things like that. So you refactor the recorded code and add checkpoints along the way. In my opinion, it's a very powerful tool, but it's not a replacement for unit tests. If you think about the cycle of development, if you're testing your whole application level, you're going to have a whole lot more code to build and to link and to run. And depending on the startup time of the application, that may slow you down quite a lot as well. I would also add that it requires a significant commitment on the part of the organization to training and to maintenance of the tests. They're higher level tests, so they have a tendency to be more brittle. But if you can use them well, and there are certainly companies that have done, they can replace a huge amount of manual testing that a lot of organizations, if they don't have good unit test coverage, they settle for manual testing, typically before a release cycle. And so Squish can, where I worked previously, we use Squish to significantly speed up our release cycle. So I am not talking about Squish, but it's important to let people know that it exists because it is a powerful tool. This summer, there was a really good talk on behavior-driven development testing with Squish. And if you're going to use Squish, I really recommend this talk. The link to it is in the notes that I'll share at the end. So the type of testing that I'm talking about is developer-written tests, where you're editing the code, you've got access to the code, and you're writing small amounts of C++ to exercise the code and test the behavior. And when necessary, to modify the code that you're testing to make it easier to test. So that's our context for today. And I want to talk a little bit about how you add tests to an existing app, because it's a question that I was asked after I'd given several talks on testing. I realized that if you haven't used tests before, understanding the starting point is really important. And the answer is you don't add tests literally to your existing main. So imagine that you have a program, which for simplicity I'll call GUI.exe. It's got a main, it's got a load of CPP and header files, and if it's a Qt application, it's probably got UI files, Qt designer files, and so on. And what you do in order to make the bulk of that code testable is separate it out into a separate library, which I've called UI.lib here. And so you change your build system so that the build system creates a library, a static library, and I'll talk about why static in a minute. And you compile and link into that library your CPP files and your UI files. And then your GUI program links, ideally just contains the main, and the build system links that library into your GUI program. What that then allows you to do is to write a separate program called, for example, UI-test.exe, which has its own main and its own set of source files that contain the tests, the assertions. So this has lots of benefits, one of which is developer productivity, because the code in the library is only built once, and then both of the executables link it. And you can be confident that your tests, when they're running, that the way that the library code, the implementation code is compiled is consistent with the way that the release code is compiled. So that's really good for safety. If there's just too much code to move to the library and you can't move all of it, then start by just moving out into a library the code that you're going to start by testing. And it's worth emphasizing at this point that if you inherit a large amount of code that doesn't have tests, you don't want to test everything. You want to start by testing the areas of code that you're going to be changing. It's too expensive and just too unproductive to disappear into a pit and test everything. You'll never release anything. So let's talk quickly about why static libraries. If you opted instead for a dynamic library, then on Windows, you would find, if you just linked your existing code into a dynamic library, a DLL, you get lots of linker errors. And then you would start Googling about DECL spec import, DLL import, DECL spec, DLL export. You would investigate how CMake makes doing that easier these days. But you'd have a whole lot of chasing your tail to fix that kind of code. Whereas with a static library, you don't need to change your source code. Similarly, your release process, if you move, this is on all platforms, if you move to dynamic libraries, those libraries remain separate from your executable. And so you need to include those in your distributions to your users. So that's a whole load of extra work to do. Whereas if it's a static library, you don't need to change your release process. So if you're starting from no libraries and just a collection of source files, and you're moving to using a library, start with static libraries because it's a smaller change, it's simpler. So nothing against DLLs and dynamic libraries. If you've got those, that's great, you're in business. But if you don't have any, start with static libraries. For the mechanics of doing that separation, it really depends on the build tool that you use. If you use CMake, then this series of blog posts by Arnie Mertz a couple of years ago will get you started. It's a very good introduction. So now you've separated out your code that you're testing into a library, how do you create the test executable? Well, the first thing is pick a test framework that you're going to be using. Here's a selection of well-known, very good test frameworks. For this talk, I've included Qt Test, which is the Qt framework, the Qt Frameworks test library. And it is really powerful for testing Qt widgets. Mainly in this talk, I'll talk about though using tests written with catch, but also in conjunction with Qt Test. Some of the tricks that I talk about for integrating catch with Qt testing will be useful as well if you are testing using Google Test or Doc Test and so on. So there's some more, it's not necessarily all specific to catch or catch 2. So let's compare and contrast the Catch 2 framework, what your test would look like, with that for Qt Test. So on the right-hand side, I've got a trivial example where my test case is testing QStrings to upper method. And in Catch, the assertion is on line 8, and it says check that string.toUpper, QString.toUpper is equal to hello. This is what that would look like in the Qt Test framework. So it's more than twice as many lines, well, about twice as many if you ignore the comment at the top. And a particular thing to say is if you look at the bottom 2 lines, you're having to generate a main in every one of your Qt Test source files. And that comes with a whole load of extra boilerplate code. And on line 5, you see you're having to create a class that inherits QObject. And each of your tests is a slot, private slot. I don't know if it has to be private, but a slot inside that QObject implementation. And your Qt test code will not work if you call Qt verify and similar qverify inside non-slot methods. So that's a really important thing to understand. So on that code, I'm not using the benefits of Qtest. I'm only showing you the overheads of it. Let's move on to another example. So here we're testing a couple of numbers. So we've got another test case, still no main. And this is the extra code. So again, we're having to create another QObject, another Qtest main, and so on. The details of this don't matter. The point is how expressive the tests are and how simple it is to add new tests. But what would that look in practice? So I've shown you 2 trivial source code examples, and you would build that using a single CMake lists file and a single main. And I'll tell you in a minute how to set up that main. Whereas with Qt Test, each of your test files is a separate program. So typically you would create a folder structure like this. So then you need 3 CMake files. And moreover, in CLine, for example, you're running a single program. You're building and running a single program. So you can run all your tests in one process. You can put debug breakpoints in multiple different tests. It's really flexible and really convenient. Whereas because of the structure of Qt test, you've got 2 different programs and 2 different lots of mock generated output as well. If you don't know what mock is, don't worry, it's detail. And so I wanted to try and give a flavour of why many people have written articles talking about how to use Catch or Google Test to test Qt code rather than Qt test, because it fits in with many people's idea of convenient development workflows. So I said I would explain how to set up your main. And at this point, I want to say that for Qt test framework, this is all hidden behind macros. You don't need to set that up. With Catch or with any other runner, you would need to set up this kind of code. So we're going to tell Catch that we want to get it to generate code that we can call from within our own main. So we define catch config runner, and we include, however you spell, including the catch header with your build layout. And then a Qt GUI widgets, you can only create instances of Qt application widgets if there is a Qt application object in existence. So we, in the main of our test program, we create a Qt application object there, and then that exists for the entire lifetime of our tests when they're running. I've sometimes seen people try and create a Qt application, destroy a Qt application in every one of their test cases, and that gets fragile. So it's better to create one in the main and let it live for the lifetime of the test. And we can pass in, or we should pass in, the arguments that our program is run with to the Qt application constructor, and then it will pick out any of the standard applications like -platform off screen. So that's nice if you're running an IDE and then running the tests and you want to, I don't know, be checking your email and not having the widgets all pop up all the time. Then you check the test results at the end. And now we need to tell Catch to run its tests. And this is how you tell Catch to create a session and run it. And then we return the result. So you could use --break to tell Catch to break into a debugger if a test fails. So it's a bit of boilerplate, but you only put it in your main. Now, in order to have some examples to talk through here of slightly more realistic code, well, significantly more realistic code, I've taken a couple of small chunks from this application, SuperCollider. It's a fantastic platform and development environment for synthesizing music, for synthesizing sounds, and composing music by algorithm. If you've seen Sonic Pi on the Raspberry Pi and the joy that brings to kids of all ages, then SuperCollider is a significant component of Sonic Pi. But for reasons I'll explain shortly, I'm going to start with a trivially small part of SuperCollider. I'm going to start with this little red square in this composite widget, custom widget, that's somewhere in the SuperCollider IDE. And we're going to be testing the behavior of this little ColorWidget is the name of the class, this little picker. When a user clicks on this red foreground square, this probably represents text color, maybe the color of an error message or something like that. SuperCollider pops up a color picker dialog, and the user chooses a new color, clicks on OK, and then in the application, the red square would change to green. So what do we want to test? Well, there's 2 halves on that screen. On the left-hand side is our custom code. This is the code that is maintained in the SuperCollider project, and that's what we want to test. On the right-hand side, this is either going to be a Qt dialog, or in some cases, it may be a system dialog provided by your operating system. It's going to be hard to test. It is certainly possible to test dialogues, especially in code that you maintain. harder for system code. It's the Qt project's job to test this. It's not ours. We want to only test our stuff. So we're going to focus on testing what's on the left-hand side. And when you start writing tests for code that you don't know, initially you start just trying to make sure that you can call the code and run it. And so that's what I'm doing here. The little black square at the top shows that I'm testing what turned out to be the initial state of the color widget, which turns out to be black. So I've got my catch test case. I create a color widget object. And in this case, I'm going to write a really trivial test that says I expect it to be black and opaque. And then I'm going to call check, which is a catch assertion, widget.color equals my expected color. When I first wrote this test, experimenting with it, it failed, and it took me a while to work out that I'd written 0, 0, 0, 0. So I'd said expect the behavior to be a transparent black rather than an opaque black. So even the act of starting writing trivial tests enables you to learn about the code that you're going to be maintaining. Now, if that fails, and when it did fail for me initially, catch writes out. So catch is brilliant about writing out the values that differ on either side of your equality check or inequality or less than, providing it's a class that it recognizes. But of course, catch out of the box doesn't know how to represent a Q color. And so it wrote out curly braces question mark. So that's what it wrote out. So I wrote some code which you can get from the approval tests Qt library that I'll talk about later on to teach catch how to convert a Q color to a string. And so this catch string maker convert technique is something that Catch 2 provides to enable you to teach Catch 2 how to represent objects that are not already known to Catch. And so I made it say that to write an opaque black as 0, 0, 0, comma alpha equals 1, which is nice and expressive of the values. You can use that for generating tests. So initially I wrote check that a string representation of the color is an empty string. Then I ran the test. I saw Catch's console output and I copied and pasted the right answer back into the code. Llewellyn Falco and Emily Bache and others call this approval testing, where you run the code and you approve the results by copying and pasting the result back into your test code. And from that point on, if the behavior changes unintentionally, you'll find out. And when you're testing legacy code, the right answer is always initially the current behavior. So that's a really important principle. Now, if we explore changing the state of the widget, what's available in the public interface of ColorWidget is a setColor method. So I'm going to create the widget as before and then call widget.setColor and then assert that the new color is red. And I treat that as a safe test to write because I can see in the interface of ColorWidget that setColor is the only public way of changing the color of that widget. And so I am going to trust that the implementation of the entire application calls via that method and it's sufficient to test at that sort of unit level. So at this point, some of you may be thinking, oh, it was quickly testing in the title. That wasn't very quick. And it's true, when you start writing tests, going from no test to the first test is always the hardest step. That's normal. There's so much to learn and to do. And almost without fail, every time you'll find adding the second, the third test becomes much easier. So the following on from that, make the first test that you write as easy as possible, because it's probably going to be hard. And then step 2 is don't give up after step 1. Try writing a few more tests and you'll start to get into your stride and you'll see the value of writing tests. Now let's look at a slightly more complex component of the SuperCollider IDE. So if I zoom in on that red box, This is how in the SuperCollider development environment, somebody can make the cursor jump to a particular line. So users can type into the spinner and then click the go button. And in the so how that's implemented, the behavior of that is the user, what we're going to test is the user typing a 1 and then a 7 and then clicking on go. And this widget doesn't know about the document model within SuperCollider. It's entirely separate from that. So when the user clicks go, the widget emits a signal 17, a signal called activated with the value 17. And what happens, for those who don't know, a Qt signal, it's a special method for announcing changes within your GUI. And there's a corresponding thing. So signals are sort of private methods that you can't call basically externally. And then slots are special methods that you can call for responding to changes. So you connect a signal to a slot, and then the Qt framework takes care of triggering when a widget announces a change. It looks at everything that's connected to that and calls the corresponding slots, the corresponding methods. So in the real application, when that happened, the cursor, the tiny little cursor there, would jump to line 17. We can't practically use that in our tests, though. To test that behavior, we'd have to make our test create an entire SuperCollider application, or at the very least, we'd have to set up a SuperCollider document and understand its document model, which is a whole heap of work. So the way we would write our test for that instead is to use a feature of Qt test libraries tools called QSignalSpy. And as its name suggests, it allows us to spy on signals and test various uses of them. So we're saying create a QSignalSpy, which is following our data member, which is a go-to-line tool widget, and listening out for calls to the method go-to-line tool activated. So in that previous slide where I talked about signals and things like that, that's really implementation details of our panel, our go-to-line panel. And my really strong advice to you is to work hard to make your tests hide as much of the implementation detail of the code that they're testing. This is not just about testing widgets, it's always across all tests. If every one of our tests knows about the finest implementation detail, in this case, the particular widgets contained within the composite widget, the custom widget we're testing, if we change the implementation, we have to update all of our tests. So you want to hide the details from the tests, you want your test to be readable and expressive, and you want to guard against changes to the implementation. And this is an example of a way to implement that. And as I said earlier, this example is very much couched in Qt test, in the Qt world. But you can think of the widget that we're testing as any chunk of code that you want to write tests for, but in order to write the tests, you'd have to poke under the hood of the thing that you're testing. There's nothing specific about this technique for testing. So in the middle, you can see I've got a class which is highlighted called go-to-line tool Fixture. And in this particular case, it contains a data member which is private, which is an instance of the widget that we're testing, the go-to-line tool. That's there. And then the test class, test fixture, has one or more public methods that are written in terms of the kinds of actions that users will do. So any application using this class is never going to want to represent users typing individual characters, but we want to write our tests in terms of user actions. And so we want our tests to be able to say type a 1, type a 7. If we say set the value to 17, we're possibly bypassing some of the behaviors that might be programmed into the widget when it's responding to individual character clicks. I've shortly got a slide that shows more use of this. I think it should make it even clearer. And then in Catch, when we're using a fixture class, instead of saying test case, we say test case method. And the first parameter is the name of our fixture class. And then the second parameter is our usual expressive, useful name of the test, that when the test fails, the test name conveys to the person checking the build logs or the developer dealing with the failure what the intended behavior was, and so what the nature of the error was. And the test then says, generate an action that types 1 into the widget. And then behind the scenes, we haven't need to change the class that we're testing at all. So here's a bit more about what the fixture would look like. And I think it's worth saying at this point that fixture in tests, it means lots of different things to lots of different people. But I think broadly, lots of different frameworks, broadly it means a collection of code that you can reuse between tests. If you're using a test framework that doesn't support fixtures, you can create your own class that provides exactly this kind of functionality. You might use it in a slightly different way, but the technique is far more general than something specific to Catch, for example. So I already mentioned that we had a go-to-line tool widget instance, and now it becomes a little bit harder to manage the lifetime of our Q signal SPI, so that's why that's a unique pointer. And it's got other details, like it's peaked inside the tool that we're testing to get pointers to the widgets, the Q spin box and the Q tool button, but they're private, they're hidden, so it's only this one place in your test code that knows about the innards of what you're testing. And now we have the really nice feature that the fixtures constructor, it's set up the widget, but then any boilerplate code that you need to do, like raise the widget, show it, set focus, anything like that, you hide away in your fixture class. And without this fixture, all of these lines setting up the SPI, doing the raise, the show, all of that stuff would be in each of your tests. Test cases, or you have to write a function that you have to remember to call in each of your test cases. But by doing it like this, that's taken care of automatically. So it's really powerful. And of course, all of that stuff is private. The data is private. In order to write this and to go from much more verbose code and then hide the details into a fixture, I started off with it public, the data public. And then I worked towards making it private over a series of steps. In Catch, fixtures are implemented using inheritance. So the test case method that I described earlier, that creates a hidden class. It generates a class with some cryptic name that you don't need to worry about. That inherits the fixture class. So you can call any public and protected methods inside your test case. I would say that's a really powerful way of sharing code between tests for minimal effort. So here might be that test case that I described earlier, the user steps written out in full. So we've got our test case method. Now, this widget needs to know how many lines there are in the document that it's representing the jumping of cursor in. And as I said, we don't want to set up a document to set that up. So we say, well, let's pretend it's a document with 27 lines. Type a 1, type a 7, click the go button. And then Q signal SPI is actually really quite complicated to call. You've got a lot of argument checking to do. That also is all hidden away. And I'll say check that my signal was only emitted once, and check that that emission contain the value 17. So that's really expressive. The intent is really clear, and you might think that a natural next test to write might be what happens if the user types 37. So if the requested line is outside the line count limit, what happens then? Is nothing emitted? That kind of thing. So you can start to explore the kinds of behaviors and corner cases that are important to test. Testing the number of times that a signal is emitted is also worth doing. I've seen errors where a connection gets lost or a loop gets created and a signal may get emitted multiple times. And that can be inefficient or can actually break the program. So those are the kinds of things that's worth testing with Qt code. That code that I just talked you through is version 3, the third of a set of examples. And so the first example, the setup code, example code in the setup is like 5 slides of code or something like that. And then the assertion is 1 or 2 lines of code. And I evolved that code through a second and then a third iteration at my talk at CPPCon this summer. And I feel that you can, I think it was important to, in this talk, to express the overall benefits of the fixture classes and that style of testing. If it didn't make sense and you want to see more of the rationale behind it, then there is a more detailed, a longer explanation in that talk. But I hope I've done it justice in this one anyway, to encourage you to look further. Now, bonus points. I talked earlier about separating the implementation details of the UI code out from the program itself. I've worked in scientific software, scientific Qt applications for many years, and it's really easy for people to be so focused on the behavior that they want to implement in the GUI that they start writing the logic, the algorithms, the data storage inside the widget code. And once you've done that, it can be really quite hard to separate the logic out, but it's really worthwhile doing it. And so for bonus points, you would separate out any non-GUI code, or as much non-GUI code as possible, into a separate lower level library, which is your model, your business logic, and so on. And then your user interface library calls code in the model library for its implementation, for its behavior. And of course, the GUI executable, that also may use model code directly or indirectly via the user interface library. And then you write a separate test program, in here called model tests, for example, and that has its own main and a different set of tests. And the general rule is you want more tests for lower level code. So you would test as much of the logic in the model tests, and then the UI tests become much thinner, and they're only testing the behavior of the widgets and not the details of what they do. Now I'm going to talk briefly about error-prone things with Qt. If by any chance you're working on code that was written in Qt 4 days or earlier, you might have signals and slots connected like this. That's very error-prone. It's easy for the connection to be wrong, and you only find out at runtime or when you get a bug report from the user. If you're working on code like this, I definitely recommend trying to switch to Qt 5 style pointer to member function connections. So here, instead of the signal and slot macros, we are saying when Qt push buttons method signal clicked is emitted, then call the quit method inside sample main window. There's lots and lots of reasons why this is a better and safer thing to do, but in terms of safety and testing, it's a complete no-brainer. The Clazy tool, C-L-A-Z-Y or Z-Y, has a way to make that updating automatically if you need to do it for lots of code. Event processing is another thing to be aware of. In a Qt application, the program's main event loop will be processing events via Qt core application process events, and you can't rely on that in test programs. So I'm not going to go into the details here, but basically know your options, know these things exist in the Qtest framework. If your test runner is Qtest, you can also use those macro-ified versions as well. If you're test runner is not Qt test, avoid like the plague any macros provided by the Qt test framework. So using Qt signal spy and things like that, that's all fine, but their macros are not designed to work in non-Qt test-driven programs. The nature of the error is your tests will silently pass, even if the code is completely broken. The first failing assertion, it will silently return from your test function, and you will never know. So it's a really important caveat. I'm not going to go into the details of this, but when I gave a similar talk to this at Meeting C++ in Germany last year, Fabian from the Qt company, I described this problem to Fabian, and he gave me some example code that showed how to redefine Qt compare and make it generate a compile time, a compilation error, if you call these macros outside of where they're meant to be used, which is fantastically powerful. And I would love to see that incorporated into the main Qt code. Once you've written these tests, you want to be running them in a continuous integration system. And the summary of this slide is make sure that your CI system has a GUI environment so that your GUI tests, your widget tests, can run. On Windows, it will probably just work. On Linux, you'll need to set up a virtual display. XVFB is commonly used, and there's lots of information about that online. And on Mac, you probably need to have a user logged in so that there's a display. You may find that if the display mechanism breaks, then your tests fail with some traceback and Qt saying it can't create a widget. In which case, look at setting up a mechanism so that tests that require an environment have a graceful way at the start of them to say, if I've got no GUI environment, then return, so that you get a message and you can fix the GUI, the display environment on the CI system, and the rest of your tests, your non-GUI tests, can go on and run gracefully. Now I'm going to talk briefly about approval tests and Qt. So if you haven't heard of approval tests before, it's a way of testing code that it saves the current state. It saves a snapshot of behavior of an object, a string, a class, as a file, as a text file. And so rather than you don't write tests that say check expected, comma, actual. You say, here's an object, verify its state, and then approval tests gracefully, conveniently, powerfully creates a text representation of that, and that becomes the right answer in your test. So it's great for large and complicated things with lots of state. Really powerful. It's really powerful that it stores its expected information separate from the source code. It keeps your source code simpler and more maintainable, and the outputs are much easier to deal with when they're separate files. You can have an XML file stored as an XML file rather than embedded as a string inside a C++ source file. It's really powerful, convenient and quick tactic for testing legacy code, but it doesn't know about Qt. This summer I gave a talk generally about the approval tests for C++ library and testing legacy code with that. So there's a lot more information there if you're interested, or ask me afterwards. At this point, I just want to mention that I have released a very small library called Approval Tests for Qt. And this little bit of the talk now is about awareness. It's letting you know it exists. So it is released containing a copy of approval tests for C++ and Catch 2, and you need to provide your own build of the Qt 5 test framework and Qt 5 widgets. And it has two goals. My first goal was to hide all of that boilerplate main function that I showed you earlier, so that if you want to use, in this case, Catch, to test Qt code, you can do that, even if you're not interested in approval tests. And I also wanted to start adding approval test support for Qt types. So those are the links, and as you can see, it's a very early version. So on the left-hand side, with those two lines, hash define approvals catch Qt, and then hash include approval test Qt.hpp, it's released as a single header. That generates the equivalent code to the code that I showed you on the right-hand side. That's it. That's all you need to do. So let's imagine that you've inherited some chemistry application that has got a table that shows you details about a series of atoms in a molecule, in a crystal structure. And the code for calculating those values is embedded inside the widget code. And you want to separate that code out so you can reuse it in other code. And you want to write a first test of the text generating code before you make a change. This is what, in that situation, the code would look like using the approval tests for Qt framework. So you create a widget that is your table, and then you call your population code to populate the cells however you would normally do it. And in tests, when you're calling existing code, however complicated the code is to call, you want to hide that away inside easy to call methods. And then we call approval test Qt, verify QTable view. So even though I'm passing in a table widget, it would work with any table view and QTable view implementation. So you see there's no actual, this is what the right answer is. And when that code is run, it writes out a tab separated file. And that file is given a sensible name automatically based on the location of the test source code and the name of the test that you're running. And the test first time around would fail because it doesn't know what the right answer is. And you use a differencing tool, and this is all set up automatically with an approval test. You use a differencing tool to copy the initial output file over to the golden output, the approved file. And then this is your expected test result, this file forevermore. I'm going to talk briefly about testing using screenshots. And we do provide in this library the ability to take and save the image of a widget and use that for testing. In general, though, it's never recommended to start your testing based on screenshots. They're fragile, they're large in the version control system. Always try and test the behavior as much as possible of your GUI code and not the appearance. But if you do need to do testing of appearance, then there is an implementation of approval tests for Qt available. So what's next? As I said, it's very early, very early for this library. So the number one priority is to guard against people accidentally using those Qt macros that I mentioned and having incorrectly silently passing tests. But mainly, I would like feedback on it. Is there any interest in it? Are there any extra types, Q widget types, Q object types that you might like approval test support for? And I'd like to add some more real-world examples to the documentation. So briefly now, in summary, the first thing here I want to say is it won't always feel like it, but it truly is never too late to start testing. However complicated the code is, it's always possible to start testing, and it's always worthwhile. When you start writing tests, and always in general, try to test smaller units of code, such as individual widgets, individual components, and test behaviors, not appearance. And as I said earlier, keep your application logic separate from the GUI code. Make your tests easy to write and therefore easy to read. Hide the details of custom widgets behind helper functions in tests, and even better, make your tests expressive and readable with fixtures. And lastly, feedback on approval tests for Qt. It's very gratefully received. That is how you quickly and effectively test Qt desktop applications. Thank you very much. Now the references, all the links and more, including a link to another library that provides a nicer implementation of approval testing images, and links to my other talks and how to get in touch with me if you want help with this or if you want consulting help. Thanks very much indeed.